Think about stacking a set of heavy, oversized encyclopedias. You don't try to slide a new volume into the middle of the pile. To reach the book at the very bottom, you must first lift off every single volume resting above it, systematically, one by one. Computer science formalizes this physical reality into a mathematical model known as a linear abstract data type, the stack. While a standard list allows data access at any index, a stack intentionally restricts interaction to a single boundary. In this wireframe container, we define that exclusive access boundary as the top pointer. This structural constraint is called the LIFO principle, last in, first out. Last in means the most recently added piece of data always occupies that active top position. First out dictates that this active top element must be the first one the system retrieves. This mapping locks the historical data. The elements buried beneath the top remain inaccessible to the top system until everything above them is cleared. Because the system only interacts with the top, it never has to scan the entire collection to find a target. This restriction eliminates search times, ensuring that every operation remains predictable and efficient. A strict structural constraint requires a strictly governed instruction set to manipulate it. Developers cannot arbitrarily inject data into a stack. They must interact through 5 specific operators. We use the push command to insert new data. As shown here, the new block slides into that singular top position. Executing a push is a mutating action, as it changes both the total size and the current state of the stack. The pop operation performs the opposite. It removes the item at the top, shifting the pointer down to the next available element. This permanently removes the data, effectively stepping the stack's history back by 1 entry. These mutating actions are distinct from state queries, which read data without changing the structure. The top operation, or peek, is the primary way to inspect the stack. Unlike a pop, a top query only inspects the active element. It returns the value while the element remains locked in place. For logic and safety, we also use the isEmpty operation. This acts as a check to verify the container holds data before the system attempts to execute further commands. Finally, the size operation provides a high-level view of the stack. It returns an aggregate count of all elements held, bypassing the top-only restriction to report the total volume. Together, these 5 operations form the complete mechanical interface for the stack. By forcing all interactions through this rigid bottleneck, the architecture ensures that state transitions are both instantaneous and highly reliable. These theoretical operations eventually encounter the physical realities of computer memory. An engineer must decide how the stack will occupy hardware, choosing between static and dynamic architectures. In a fixed-size architecture, the limits are absolute. On the left side of the screen, this stack uses a static array. Its maximum capacity of 5 slots is locked in when the program is first compiled. This predefined limit creates a vulnerability. If you exceed the capacity, the system fails. This failure mode is known as an overflow. Attempting to push a 6th block into this 5-slot grid triggers an overflow error, halting the operation. The opposite failure is the underflow. If the stack is empty and the system attempts to pop an element, it tries to pull data from a void, triggering an underflow error. To bypass these rigid limits, engineers use a dynamic size implementation. On the right side, this dynamic stack uses a linked list. It doesn't rely on a pre-allocated grid. Instead, it creates discrete nodes connected by pointers. This stack grows and shrinks at runtime, allocating fresh memory independently for every push. Because it scales on demand, this implementation will not hit an overflow as long as the machine has available RAM. This is highly efficient for unpredictable workloads, as the system never hoards empty memory slots. However, there is a trade-off. Each node requires extra memory to store the pointer, the address of the next item in the chain. Static arrays use less memory per item, but they waste space if the stack isn't full. Balancing these trade-offs is a primary responsibility in software engineering. The choice between an array and a linked list determines not just the memory footprint, but how the software handles critical failure conditions. These internal mechanics drive the observable behaviors we rely on in every application. The stack is the primary model for handling state history. It is the ideal tool for sequences where the most recent action must be resolved before the system can return to a previous state. In this text editor, every word you type is captured as a discrete state and pushed onto a history stack. By capturing these actions sequentially, the application builds a perfect chronological record of the user's input. When you click Undo, the system executes a pop. The most recent state is removed from the stack, and the document reverts to its previous appearance. This same logic governs how your web browser manages your navigation history. Clicking a link pushes the current URL onto the stack. Clicking the back arrow pops it off to reveal the page you were on just seconds before. This logic even extends to the core of computer processing through the call stack. The call stack tracks active subroutines, ensuring the processor knows exactly where to return after a function finishes. When function A calls function B, function A is paused and pushed onto the stack to preserve its current variables and location. Function B now sits at the top, utilizing the processor's resources until its task is complete. Once function B finishes, it is popped off, allowing function A to resume exactly where it left off. The stack is more than a simple container. Through its LIFO constraint, it serves as the mechanical engine that allows computing to manage nested logic and maintain a precise record of execution.